talk about geometry and dynamics of free-by-cyclic groups.
All right, thank you to the organizers for the opportunity to speak here, and thank you all for coming. So I'm going to talk about one project with Dowdall-Kapovich and Kfir-Leininger, and it's sort of a big project in the sense that there's many pages we wrote about it. So since we're both talking, we're going to tag team and try to tell you lots of things. So anyway, but the talks will be somewhat, disjoint from each other and focus on different aspects of the project. Let's just introduce the idea is to study free-by-cyclic groups. Okay, so what's a free-by-cyclic group? Okay, so that's a group G that looks like a free group, semi-direct product with a cyclic group. Okay, so the semi-direct product is over some automorphism here. And if you forgot how semi-direct product goes, let me just remind you. So it's the group generated by the free group with one extra generator, call it R, and it has the relations that R acts on Fn and conjugate by this automorphism. So for every G in Fn, you assign this conjugator to be the image of G under your map. Okay, so here, this phi is some automorphism of your free group. Okay? And let me right away say that's sort of a lie. It turns out the isomorphism class of this group only depends on the outer automorphism class of this element. So I'm really going to think of it as an element in out instead of op. Okay? But not too big of a difference there. So what's the basic question is, look, here we have this group, nice semi-direct product group that I wrote. And the question is, maybe I could write it as a semi-direct product like this in other ways. Okay? Maybe why is this free group special? Maybe there's some other, free subgroup of it, and then I could write it as a semi-direct product in some other way. And so the basic idea is to try to understand how you can do that, and what can you say about this? Okay, so are there other ways to write G as free-by-cyclic? The basic question. Okay, how are we gonna, even think about this or get started on this question? Maybe you need some way to kind of parameterize possible ways to write G as a semi-direct product. So it turns out, what you should think about is cohomology classes of G. So let's consider something in the first cohomology of G. I'll often think about with R coefficients here, and
What's that letter? There.
Yeah.
Just do that.
So if you don't like group cohomology, this is really just homomorphisms from your group to R. Okay, so it's a very simple thing. It's a vector space. I'm going to write it as cohomology just because I kind of like doing that, but you can think homomorphisms. Okay? It turns out these things are sort of important for trying to think about this question. So let's say that U is primitive integral. Okay? Which I'll often denote by PI for short. So that means that the image is exactly Z. Okay, so the image is some subgroup of R, and I want it to be exactly Z. All right, not just so the integral means you land in Z, and primitive means it's surjective onto Z. Okay, so if you have such a cohomology class, what can you do? It gives you a couple things. Well, first of all, it gives you a splitting. So by splitting, I just mean a short exact sequence, right? So, I have my map to Z here. It's surjective by assumption, that's what primitive means. And then it has some kernel. And, I have a short exact sequence like this. Okay, so that's a splitting of my group. And when you have a splitting of your group like this, you also get an action of this group on this group, right? So that's called the monodromy. So the monodromy is an element in the outer automorphism group of the kernel, and it's defined by, if I take something in the kernel, what's its image? It's just conjugate by something that goes to 1. Okay, so how do I define this automorphism? I just take the generator here, I choose any lift, and then conjugation by that defines an automorphism of the kernel. And that's only sort of well-defined up to inner automorphisms, which is why I get something in out instead of on. Okay. So this is kind of nice. Every cohomology class, goes give me a splitting and a monodromy. And sort of my question is, when is this maybe a nice splitting? Like a free-by-cyclic group splitting. Okay? So let's try to address that a little bit. So here's a question. When is the kernel finally generated? That's maybe a nice first start. The kernel here, we have this this finally generated subgroup that we're doing a seminar product with. So maybe I want the kernel to be finally generated. In fact, I'm going to think about a kind of more general thing. So some dots here. So I want it to be finally generated, not maybe not finally generated, but over the monoid generated by the monodrome. Oh gosh. Okay. So that just means there should be some finite set of things in the kernel such that up to prior to those things and acting on them by the monodromy, I can get everything. Okay? So that's all I mean here. It's just sort of a slightly weaker thing.
What's that subscript on the outside there?
Oh, that's plus. That's what I mean by the monoid. So you're not allowed to take inverses.
Right.
Yeah, that's what I mean. Okay, so that's maybe a weird thing. Why would you want to think about this crazy monoid? Well, it turns out this is equivalent to some kind of classical condition called being in the Bernoulli stable invariant. Okay, so this is equivalent to you being in what's called BNS-invariant of group G, which has some definition, but for integral classes, it turns out to be exactly what I wrote down. Okay, so this thing, is an open cone in the first cohomology of your group. All right. So this is something introduced by Bernoulli stable. This is sort of important invariant of group, and this is maybe you want to know when you're in that BNS. Okay. So let me tell you another way to think about this. I don't know if anyone likes thinking about these finally generated things over monoids, but it turns out this is equivalent to being able to express your group as an HNN-extension in the following way. So it's equivalent to being able to write your group as an ascending HNN-extension where this Q will be some finally generated subgroup of the kernel. And this phi is just the restriction of the monodromy to that finally generated subgroup. And it preserves that subgroup. So it acts on it like that, and it's going to be some injective. So if you forgot what an HNN extension is, it's exactly a group with this sort of presentation where I don't require it to be an automorphism. It's only required to be an injective endomorphism. So that's an HNN extension. So it turned out being in the BNS-invariant was equivalent to finding a finitely generated thing in the kernel such that the monodromy sort of preserves it. Okay? And that's this condition. Okay? So, all right, so maybe you might want to know that. But we wanted to write it kind of as a free-by-cyclic group. And so far I've only talked about finally generated things. So it turns out that in this situation, as soon as you have finite generation, the thing has to be free. Okay? So let me maybe point out that kernel of U finally generated, or this QU finally generated, implies that it's a free group. Okay? And that sort of follows from some work of Bieri. I think he showed that in this sort of situation, we have a free-by-cyclic group. If you can express it as sort of an ascending HNN extension or a semi-direct product over a finally presented group, and that finally presented group has to be free. And then free-by-cyclic groups are coherent, it's proved by Fein and Handel, which means that all finally presented subgroups are finally generated. Sorry, finally generated subgroups are finally presented. So as soon as you know finally generated for these things, you know they're finally presented, and this work of Bieri tells you different. Okay? So really this finite generation business is all we need to get sort of free groups in these extensions that we're looking
Can I ask a basic question? So, using the word monodromy, I'm a manifolds person. So, should I be thinking G is a three-manifold vibrating over the circle?
Yeah, you should be thinking that. So this is, I mean, that's sort of the motivation for this project, is the situation where you take like a surface and the homomorphism of the surface, and then you do the sort of analogous semidirect product where you have a surface group semidirect Z, and that'll be the fundamental group of the mapping torus. Of that fiber mapping torus, exactly. Yeah. And these are like sort of the algebraic realizations of the monodromies of other fibrations.
So then outside, I guess I lost the thread. So this kernel is finally generated over the monoid. So as by itself, it may be infinitely generated.
Yeah.
But now you're saying it's free. That stuff in red, is that, when you say finally generated, that's still over the monoid?
No, I just meant
That's
if it
really
turned out
finely
that the kernel itself was finally
Really
generated,
actually finally generated.
then it would be free.
Okay.
And if you can find this sort of finally generated subgroup of the kernel, it's automatically free.
Okay.
Yeah. Okay, great. Okay, so that's sort of an algebraic kind of question you might want to ask about these different splits. This is sort of like, when can you find other nice splittings of your group? Is it free-by-cyclic or maybe an HNN-extension over a finally generated free group? Okay, so maybe you might want to try to study this. Another thing you might want to try to do is to study these monodromies. Okay, so right when we have these cohomology classes give us splitting, so we thought a little bit about when that might be nice. What can we say about these monodromies? Okay, so here's maybe another question. Question 2 is to study the monodromies. So I don't know, what do you want to know about them? Maybe are they related to each other in some way? Okay, so there's a couple ways you can think about this. So let's tell you a few things. So first of all, if I have a class in the BNS-invariant, which so something where I can write an HNN-extension like this over there, that's primitive integral class, then I know that I can write my group as this HNN-extension, and I have this sort of injective endomorphism of a finally generated free group. Okay, so I can take this thing, and I can look at its stretch factor, which I'll call lambda u. This would be the stretch factor of that thing. So that's going to be the supremum of the things in that subgroup of this quantity. So I take my injective endomorphism, and I take powers of it, and I apply it to some element, and then I just see how fast that grows in sort of word length, the conjugacy over here. Right, so for every element B, I calculate this limit, and I just see what element gives me the biggest thing, and I'll call that the stretch factor. Okay, so this is some just number that measures how much exponential growth is there in this injective endomorphism of the free group. Okay? All right, so that's something.
It looks like this QU kind of, you make choices for this.
Oh,
QU.
that's a very good question. You make choices for this QU. Yeah, in fact, so this is not at all unique writing the group this way. It's a very good point. So then you might be worried about my definition here because there was lots of choices involved. Well, it turns out while this group you get is not could change, this number is always the same. So any way you write the group as an HNN-extension like this, you always get the same number. So that's a well-defined thing.
Even if you fix QU can be.
Huh?
Even if you fix QU can be is not.
Yeah. Even if you fix U, in the case where this is sort of injective but not surjective, you can find lots of different finally generated subgroups inside of the kernel with this sort of property. Yeah, it's kind of weird, but it's if you just write it down, it's not that hard.
And in Picker, it doesn't depend, you chose a generating set, it doesn't depend on the generating set, and all those things like the start factor and stuff.
Yeah, no, it doesn't depend on, for this word length here, it doesn't depend on the generating set.
The word length, the limit doesn't, right?
Yeah, and the limit, the word length does, but not in the limit. Okay. Okay, so that's something you might want to know is this exponential growth rate of these kind of monodromes. So let's do the following thing. Let's propose scaling. It's sort of the right thing to do. Where if I multiply a primitive integral thing by k, I'll just define this thing to scale by 1 over k. Okay, so somehow that's the right way to scale, and then that gives you a function which I call in the set Q BNS to G to R plus, and this is just the things in BNS where the image is discrete. Okay, so everything with a discrete image, I can scale it by something so that the image is exactly Z, and then I use this definition. Okay, so I get a sort of well-defined function on the BNS-invariant, on the rational points of the BNS-invariant. Okay, so maybe you want to try to calculate this thing, or maybe you want to know how it behaves. Right, that's sort of how are these different monodromies related to each other. Another thing you might want to know, because it's very vague, right? So we started with a monodromy of the free group, which I call
What do you
Phi.
mean discrete?
I mean discrete image, a discrete subgroup of R.
But isn't the image of U Z?
Oh no. Yeah, let's see. So the BNS-invariant lives inside of
Oh, so
automorphisms.
this U is not the same U as before?
Yeah,
Okay,
no, it's not
okay.
the same U.
So this U is varying over the whole.
Over the whole
BNS.
cohomology, over all of
Okay.
BMS.
All right.
Yeah, exactly. So.
Thanks.
Okay, so we built our Free-by-cyclic group with a particular monodromy, which we called Phi. And you might want to know, well, if I started with something nice, are these other things nice? And that's a sort of vague question, but I'll write it down anyway. So if Phi is nice, are all of these other things other monodromies nice? Okay, so that's another kind of question.
Could you just give like 2 words about what you might mean by nice?
Yeah, so for example, Matt's talk yesterday, he talked a lot about fully irreducible automorphisms for free. So maybe, that's a good example. Yeah, but you can choose your adventure, what you might want to. So, the may not be what we end up talking about. Okay, so those are sort of the questions I want to try to address a little bit in this time. And so that's sort of a very algebraic approach, I think, to this thing. But it turns out there's kind of a parallel topological and dynamical picture, which I want to introduce now. Okay, so now I want to make a few assumptions. So this will be like maybe some nice assumptions on this thing. All right, so already, so let's assume this automorphism we start with is represented by an expanding or an irreducible expanding train track. Okay, it's kind of a mouthful. So let me explain what I mean by these assumptions. Okay, so to say a free group automorphism is represented by something, that just means I have a graph map. Where my graph, is realizing my fundamental group, my free group, and the induced map of my graph map is the automorphism. Okay, so it's just a topological realization of that thing. To say it's irreducible just means that the transition matrix is irreducible. Okay, so that just, the transition matrix, I just records which edges get mapped over which other edges. So it's irreducible means for any coordinate in the matrix, there's some power where it becomes non-zero. That's all. Expanding just means that the spectral radius of that transition matrix is bigger than 1. Okay, so they actually have some exponential growth going on. And then the most, maybe confusing if you've never thought about it before, is this train track condition, which turns out to be very important. It's a nice dynamical condition. And it says that every power after the k is locally injective on each edge. And that should be for all iterates, k, greater than 1. Okay, so that just means if I look at an edge and I look at all of its images, it's never getting like sort of folded in the middle. It's always locally injected in every part of the edge. So that's a nice condition. I mean, if you are familiar with the surface world, the mapping class group world, this is sort of like an analog of a pseudo-Nassau representative in some sense.
Which part of this parsing applies to which part of the description?
Oh, it's line by line.
Line by line.
Yeah. Yeah. Line by line. Mhm. Okay. So yeah, maybe think pseudo-Nassau representative if you like mapping class groups.
You say what spectral radius greater than 1 means again?
What was that?
What's spectral radius greater than 1?
Oh, that's the spectral radius of the matrix.
Like in analytic sense?
Yeah, I want like
The
the
radius of the
eigenvalue, the largest eigenvalue.
Yeah, okay.
Large like
Largest eigenvalue, yeah, for example. Okay. So if you have such a thing, then what we're going to do is build a mapping torus of it. Okay? So let's take the mapping torus. So that's just this graph across the interval where I quotient out by, I glue the top to the bottom by the map. Okay? So let me try to draw you a picture of an example of that. Maybe I can fit it here. Okay, so this is a graph, and maybe I have a map from this, like from the graph to itself in the following way. So I should label the edges, A, B, this edge is D down there. This is C. And I want to send these, edges to these ones by the following labels. So I'll send this edge to D. I'll send this edge to A. I'll send this edge to, B and A. And I'll send this edge to B, A, D, and then B, A, C. Okay, so these sort of arrows going like this. Okay, so that's an example of such a a graph map, and it turns out it it satisfies these conditions if you wanted to work it out. It's a good exercise. Anyway, so now we're going to build the mapping torus, which just means I take the product of this, and then I glue the top to the bottom. So this is not really the object we think about in the paper. We actually deal with this other thing called the folded mapping torus, which I don't want to describe, but let's just think about this for the purposes of the talk. And I think I don't not really even going to lie if we're going to think about this. Things still kind of work in the situation. Okay, so that's a nice thing. What is this thing? So it's a KG1 space. Turns out it's the fundamental group is my group G, and all their homotopy groups are 0. It's a 2 complex. And the other important feature is that it has a semiflow. Psi t from x to itself. Okay, how does the flow work? The flow just goes up. Okay, so if I start somewhere in this thing, I just go up until I hit an edge. I hit the top, and then I just look at my label. I see where I go down there, and I keep going up until I hit the top again, and I repeat. Okay, and I can't go down because if I go down and I hit this edge A, am I supposed to come out here? Am I supposed to come out here or here? I don't know. Okay, so I only get to go up, not down. It's a semiflow. Okay, so this is some topological thing, topological space with a nice flow on it. So it's a nice dynamical system. And turns out it has a lot to do with these algebraic questions I was talking about before. So there's sort of an algebraic questions about G. G, that's like sort of a world you might think about that we were talking about before. But then there's also sort of this picture of the dynamics of this space with its flow. Okay? And it turns out these are pretty related to each other in interesting kind of ways, which is what we're going to try to explain in these talks. And I'm going to kind of focus on this half of the story for my talk about these algebraic questions I was posing before. And in Chris's talk next, he's going to, I think, focus more on this picture. Okay? So that's the plan. But I want to tell you a little bit about how these are related to each other. So the key thing here key relationship is cross sections in my mind. So let me tell you what a cross section of this thing is. So a cross section of this dynamical system here is a finite graph sitting inside of X, I'll call it theta. And it should be transverse to the flow. So I just mean, this is some too complex, and like every two cells sort of foliated by flow lines. And I want my graph sitting inside to be transverse to all those lines. Okay, so that's what I mean. So it should be transverse to the flow, and every flow line hits it infinitely often. Okay, so it's sort of a graph that I can find sitting inside where every flow line comes back. Okay, so that's a cross section. For example, like here I can draw one for you. If I look kind of halfway inside of here, there's there's this copy of my graph, for example, sitting right there, and that's a cross section. Right? You can just sort of see the graph is transverse to the flow. Everything gets in it. That's a good example of a cross section. Okay.
Why do you need to say infinitely often?
Huh?
Why do you need to say
I probably don't need to say infinitely often. Yeah, I don't know. It just depends on what you mean. Yeah. So I don't want to mean like you take like a bi-infinite flow line and that it only hits it once. I mean like anywhere you start, if you flow, you hit the graph. That's what I mean. Okay. So you can think about this in other
You
ways.
said halfway when you did that picture. Is that
The halfway doesn't
did you
matter.
literally mean halfway, or
No.
every t between?
Every
zero and-
t,
Yeah.
yeah.
Are there maybe others, or is that all?
There's maybe others. Yeah, it's a good question.
Well, I
Yeah.
assume this is the motivation behind the term cross section.
Yeah, that's the sort of motivation. But maybe there's others, exactly. Yeah. Okay, so let me just tell you a couple other things a cross-section gives you. So really you get a first return map. Right, if I just start somewhere on my cross-section, I just flow until I hit my cross-section again. Right? By assumption, I'll always come back, so I get a map. So I get a map. Okay, and also it turns out, once you have this map, you can kind of build a fibration in some sense. So a map from the space to the circle, that's a local diffeo on flow lines, and where the cross section is exactly, a fiber. Okay, so you can sort of build a nice map to the circle that's kind of like transverse to the flow in a certain way, where the flow lines are, it's local diffeomorphism on the flow lines, and this cross section is really just a fiber. So it's really just sort of like a fiber and a fibration of the thing. If you like thinking about manifolds, that's really all it is. Okay. All right, so it'll give you these nice things, and yeah, so that's nice to think about.
So is the thing to be thinking about here like other vibrations of
Yeah, so you should be thinking, if you're thinking about the free manifold picture in your mind, you should be thinking about other vibrations of a fiber free manifold. Exactly. Okay, so notice,
But it's not like all of the vibrations. It's like a special class of other vibrations.
it's special class of
They're kind
vibrations.
also
It's ones that play
transverse.
nicely with this flow.
Yeah.
Exactly, yeah, it's not all vibrations, but it's ones that, this sort of transversality to the flow is important. Yeah. Okay, so look, a map to the circle, so that's, homotopy class of maps to the circle, that's the same thing as a cohomology class, right? I can just pull back, the generator from the first cohomology of S. So this map to the circle gives me a cohomology class. Okay, so there's a duality here. So I say that I say that the cross section is dual to this cohomology class. Okay, so every cross section picks out a dual cohomology class. Okay, good point. So a natural question to ask would be like, what are all the cross sections? You know, I just drew one. Is that the only one? Are there more? I don't know. Okay, so that's the next question. And question 3. What cohomology classes are dual to sections?
Is there more than one fibration of a cross section or no?
One of these maps.
Do we make a choice there, or is that?
Yeah, there's sort of a choice. I mean, it's
Okay.
kind of only going to be well defined at the homotopy.
Okay.
You have to make lots of choices.
Alright.
Yeah.
So then this duality is,
But this cohomology class is well defined.
okay.
It turns out. Yeah. I mean, the particular map you get, you know, you can wiggle it around, but you always get the same cohomology.
So would all the fibrations that are dual to a given cohomology class would be homotopic, or what's the?
Yeah.
Okay,
Yeah.
alright.
Okay, so this is a very natural question you might ask once you think of this dynamical system. Okay, and turns out it's related to these other questions I was asking before, the algebraic perspective. So, how does that work? Let me just tell you this proposition. If U is dual to a cross section, theta. Oh, by the way, like so, here I wrote x, here I wrote g. This cohomology is the same. It's kg1, right? So I'm just going to go back and forth. Okay, so if I have a class that's dual to a cross section, then I'm in the BNS-invariant that we were talking about before. Okay, so there's this sort of connection between this dynamical property and this algebraic property. So how does that go? Just maybe really quickly. You just use Van Kampen's theorem. So, you apply Van Kampen's theorem to the space X with this sort of graph sitting inside of it, and you find that G, which is pi1 of X, has this presentation where the fundamental group of the cross section generated by one extra thing. You have this presentation. It looks like the sort of HNN-extension presentation you had before. But it's not an HNN-extension because HNN-extensions, you require this map to be injective. Otherwise it's sort of a nightmare. Think about this thing. So there's no reason why this first return map should have an injective map on fundamental group. So what do? You just kill the stuff that, is in the kernel. Okay, so it turns out you just sort of take this group now, and I mod out by everything that's in the kernel of that map. And maybe I have to do it for like all powers. Okay, so I take all the kernels of iterates of my map, I just kill all those things, and this presentation sort of factors to a presentation for this quotient group, okay? In sort of a very simple way, just the natural thing. Okay, so this is like the induced map on the quotient. Okay, so you just kill this kernel, and now the point is, after you kill the kernel and you pass this quotient map, now it's injective. That's not too hard to check. Okay, so this is going to be a nice HNN extension here. So I'll call this thing, this is Q. U, it's of course finally generated, right? Because it's a quotient of a finally generated group. And I just told you that this thing here, which I'll call phi, is injective. So look, I just wrote my group as an ascending HNN extension of a finally generated thing. Okay, so that was equivalent to being in the BNS-invariant. Okay? So that's kind of nice. These cross sections give me things in the BNS-invariant. Okay. So that's a key example of one of the connections between this dynamical world and the algebraic. And now what I'd like to do, instead of just asking lots of questions and introducing lots of things, is maybe try to start answering some of these questions. So to do that,
That group, the quotient is still free? Is it not even free?
it turns out it's free. Yeah, so I mean, if you believed me before about this thing about finally generating subgroups have to automatically be free, then you can use that. But you can also just prove that directly. I mean, using the fact that this is a free group and free groups are Hopfian, and this is like, anyway, so you can like, this is isomorphic to an image of this free group inside of itself. It's not too hard. You can check this. Okay, so when I start kind of trying to answer these questions, remember I just erased there was this algebraic world and this dynamical world. And what our strategy is we sort of built a thing that sort of knows a lot about the dynamics of this thing. And then it tells us about some of these algebraic questions. So I don't want to tell you the thing that we built, kind of the machine, and which is a polynomial for that dynamical system. Okay, so we construct a polynomial for this system. So let me tell you what it is, and then I'll tell you what it tells you. Okay, so how does the construction go? So the construction is the following. I take my mapping torus, X, and I go to the universal free abelian cover. Okay, so it's just the maximal free abelian cover. So here, the deck group is the largest abelian quotient of my group. So that's, I'll call it H, is just the first homology of my group. That's just the abelianization of my group, and I want it to be free abelian, so I mod out by the torsion. Okay, so it's some cover with deck group, this, abelian group, right? So this is isomorphic to Z to the V for some V. So V is the first Fedde number of G. Okay, great. So I do this, and then I lift the semiflow, something like this. You just lift it, it's not too hard. And I consider the pre-image of my graph. Right, so remember, the mapping torus, I erased it, but it was this sort of mapping torus of a graph gamma. So gamma I could view as sitting inside of there, like the zero level set, and I just take the pre-image of this graph. So that's going to be some graph sitting here. Okay, maybe I can try to draw you a picture of that, in fact. So for this example, which I unfortunately erased, but maybe you can remember, so it looks something like this. So I turned my head, sideways now. So that's what it looked like. And so the free universal cover looks kind of like this. Free abelian cover, a little bigger. Goes on, and then there's other copies of this. Okay, so now if I act by t shifting this way and x shifting this way, so I have this z2's worth of symmetries here, and you can imagine if I quotient by those things, right, if I take this accordion and sort of collapse it, I just get this graph here. Okay, so this is what the cover looks like. All right, so in this case, h is zt plus zx. It's generated by t and x, and I've sort of chosen a nice basis. Okay. So that's great. So we have this thing. So now I want to make a definition. Call it T of gamma hat. So this is going to be the free Z module on edges of gamma hat.
So what's X in this picture?
X is the map. X is the dex transformation that shifts up. It's like just on the blackboard I have shifting up, and I have X is, this is little x, it's not big X, sorry. It's just the two generators of the difference. Okay. Yeah, so T gamma, this is the free Z module on edges of this thing, so all those edges I drew, like free Z module. But then I want to impose some relations. So the relations are that E is equal to the sum E1 up to EK if E flows onto the edge path E1 through EK. So that's, what does that mean? That just means if I have an edge here, and I apply the semiflow, so I take my edge and I flow until I hit my graph again, maybe I'll end on some edge path. And I just declare that edge to be equal to that sum of edges, okay, in this module. Okay, that's the thing I can do. So that's my module. Okay, so why, great, what is that good for? I don't know. So let me tell you a couple things about it. So it turns out it's finally generated. That's not too hard to see. So in fact, this thing is finally generated. Okay? So let me tell you some generators. So if I just take, look, the quotient is some finite graph. So I just take a preimage of each thing, right? So maybe I'm going to label these correctly. So I'll call this A, call that C, I'll call this one B, and this one D. Okay, so those four things, and if I move those around by my deck transformations, I can get to anywhere, right? So every edge gets a label. Oh, sorry, you should be complaining. I meant finally generated as a ZH module. Okay, yeah. Okay, so H acts on this picture, right? It acts on the edges, so I can view it as a ZH module. Okay, and if I do that, then it's fine. All right, so these things are generators, and everything else gets a name, right? So for example, I do this crazy thing where the names change by the inverse. So I call this T inverse C, okay? And I'll call this like X, no, sorry, I'll call that TC, and I'll call this XA, for example. Okay? So I apply T inverse, that takes me here to here, so I call that TC, and that's XA. So those are the names of other things. Okay, so it's finally generated, and the generators are those things I wrote there, A, B, C, and D. Okay, it's better than that, in fact. It's finally presented, and that's also not too hard to see. Okay, if I just write down sort of a relation for each one of these generators, you can move those around and you can generate all the other relations. So let me just write those down, for example. So A, we forgot what the map does, so I'll just tell you. A maps to D, I think. So I get a relation that XA equals D. Right? So this edge down here labeled XA, if I flow it up, I claim it lands on this edge D. So that's a relation. And similarly, XB, I claim if I flow it up, it lands on A. XC lands on T inverse A plus B. And XD, if you remember, was sort of complicated. D went to BAC, BAD, and this goes to T cubed B plus T cubed A plus T squared D, it doesn't really matter, plus T squared B plus TA plus TC. Okay, whatever it is. All right, so I get some relations. And it turns out, this gives you a finer presentation of your module. All right, so let me write that down. So the presentation looks like this, right? It has 4 relations and 4 generators. Okay? And there's a presentation matrix. So what is the presentation matrix? If you just take these relations and write them down, you get something like this: xi minus at, where at is this matrix. What it is. Right, so this is the first row. It says that XA is equal to D. So that's like what XI minus that D here, that one is for D. Okay. And so I'm just writing down what that matrix is. So 1, and then some complicated thing. Okay, no one really cares what it is. Okay, but it's something. Great. All right. So, all right, great. Now I have this final presentation of this crazy module that we don't know why we're thinking about it yet. Okay, so, but now what can I do? So now I'll make another definition. I declare M to be the GCD of the fitting ideal of my module. Oh my gosh. Okay, so finally presented modules have these things called fitting ideals. Maybe you knew that. I didn't really know that until recently. But don't be worried. A fitting ideal, what does it mean? It just means take a presentation for your thing that you assume is finally presented, and just take the determinant of this guy. That's all it is. Okay? So this is equal to the determinant of this matrix. Okay? So that's my definition of this thing. And this is an element in my the ring for my module, Z adjoint H. Oh, okay. All right, so this is the thing you do. And then, so we call this the McMullen polynomial. This is our polynomial that we.
So it's the characteristic polynomial of the presentation matrix.
Basically, yeah, it's basically what it is. That's a very good way to think about it. So in some sense, this is really like the transition matrix for my graph that I initially had, but I lifted to this universal abelian cover and I sort of decorated it with labels from the deck group. So this, you should think of this as sort of the presentation matrix for this sort of lifted map. And this is really just the characteristic polynomial of that matrix. Exactly.
Why do you call it the McMullen polynomial?
We call it the McMullen polynomial because this whole, this was sort of inspired by some work of McMullen in mapping class groups where he defined what's called a Teichmueller polynomial. So he defined a Teichmueller polynomial to sort of study vibrations of three manifolds. And so we were very much inspired by his construction, and that sort of motivated doing all this stuff, and so that's why we call it McMullen.
So this is well defined up to like open by units or something?
It's well defined up to
Just like
units.
Alexander polynomial?
Yeah, it's well defined up to units.
And so how many variables? I mean, it's T and then whatever the rank of.
The variables are,
Depends.
it's whatever the size of H is.
Right.
So it's polynomial in ZH. So H, its rank is, the first Betty number of G. So that's how many variables it is. So you think of it as like just a Laurent polynomial in that many variables.
So what's the largest real eigenvalue of that bigger than 1? Is that-
Oh, I don't know, because it's not a, it's not like a polynomial that I would find roots of. I really think of it as like an element of this group ring. If you thought of them as actual like variables and I tried to find it better. But we'll get to that in a second, in some sense. Okay. So better strive ahead, because we're running out of time here.
And the reason to write it as GC is the ideals because it's well defined. That's in all these things.
Exactly. So it's a well-defined thing. It doesn't, that's the point of the fitting ideal, is it's a well-defined thing. It doesn't depend on what presentation you use. It's up to you guys. Okay, so that's the construction. Great, so now I have, 10 minutes to tell you what it tells you. Okay, so so the first thing it gives you is an open convex cone, which we'll call CM, sitting inside of the cohomology. Remember, we think you had a cohomology before. How does that work? Okay, so up to units, I can write my polynomial is 1 plus something. I can take, for instance, I'm going to take the leading term here is like x to the 4th. So I'm just going to divide by that, which I can do up to units. So this will be sort of the x to the 4th term, and then I'll have some other stuff. All right, it's a finite sum. A1, H1 plus up through AK, HK. So these AIs are integers, and the HKs are elements of the group. They're not the identity. So this is sort of, 1 times the identity. That's that term. Okay, so I can write it in this fashion. And then the cone is just the cohomology classes that, look, I have a bunch of homology classes here, right? These are elements of H. H was like the homology of my group. If I have a cohomology class, I can eat those things. That's what cohomology classes do. So I can require that all of these things are negative. That's my rule, okay? Okay? So which is another way to say, eating this one, I get 0, right? You eating the identity is 0. So this is really saying that this guy's the winner. That's all I'm saying. So I picked out a guy, and I want him to be the winner. That's my claim. So
like AI, HI is a consider or just HI?
just the classes. I don't care about the coefficients. Okay, so that's one thing. Another thing is these specializations. So if I have a class, U, now, let's suppose it's a primitive integral class, for example, then what I can do is form the specialization I'll call m sub u. So this is just going to be a polynomial in one variable. And what polynomial is it? I just, again, I take these numbers and I put them in as the exponents. So I do 1 plus a1 y to the u h1. So I just eat the homology class, I use them as the exponents, and I get this new polynomial.
Can you say again how you chose which one is 1?
Mysteriously, I don't know. It's
I mean, that'll give you different cones.
yeah, you have to choose one, and you have to know what to choose. So really, in this definition here, I sort of chose a nice basis, and x was the one that sort of, I had these different copies of the lift of gamma, and x was the one that sort of shifted between them. So that's how I chose x, and then I used this basis, and then I chose that as the leading term. Yeah. So there were some choices involved, but I didn't really explain. Okay, so anyway, you get this specialization, and this is just a normal polynomial. Right? It's just a regular polynomial in one variable.
So the power, that's a power on y?
Yeah, there's
Okay.
y to the power of whatever this number is. So this lives in z adjoin, y plus or minus 1. It's a, an integral around polynomial. Okay, so then I could look at HU I'll declare it to be the logarithm. So now we have an actual polynomial, and I can look at the spectral radius, or I can look at the largest group, the absolute value of the largest group, whatever. So of that polynomial. And that's some number that I could look at. Okay, great. So this is really what the polynomial is telling me. So it's telling me this cone and this sort of function. Okay? And these special polynomials. So, all right, great. Why do you care about that? I don't know. So let's keep going here for a few more minutes. So first of all, this is a nice function as it turns out.
To define the specialization, we're choosing u from that cone?
This is just for any
Okay.
u I could choose, yeah, if I wanted. But it turns out, it's a very good question. So McMullen showed that if you look at in the cone, a very nice thing happens, which I'll not write down. So H extends to a convex, real-analytic, homogeneous. So the homogeneity here, I mean, is the following. So if I take k times something, that gets pulled out as 1 over k. Okay. So that's sort of homogeneous function on the cone. So if I look at the cone, it extends to the whole cone, and it is very nice. Okay, so they're sort of tied together this way. And also, h goes to infinity at the boundary of the cone. Okay. So that's very good. Okay, a couple more things to say. All right, now let's. All right, so I told you about this construction of this polynomial. Seems maybe a little unmotivated if you've never thought about these things before. Why did we do this weird construction? Take this module and take the fitting ideal, blah, blah, blah. We have this cone and this function. Okay, what is the relationship to these questions we were talking about before? So now let me finally, in the last few minutes, tell you some results. Okay, so again, this is joint work with Dowdall-Kapovich and Leininger. And first result is the following, that this cone that you get is the cone of sections. Which I'll call fancy S. So that's just the convex hull of sort of positive multiples of classes dual to sections. Okay, so remember we had this idea of a cross section to our thing, and every cross-section gave you a dual cohomology class. So now I have this set of cohomology classes, and I'm basically just taking their convex hull. And the claim is that that convex hull is exactly this code. That's the polynomial. Okay. So that's the result. And I think, you know, I think that's a little mysterious and kind of surprising, you know, like why this sort of arbitrary seeming construction of this polynomial, this fitting ideal business, why should it have anything to know anything about all the sections? So that's, I think Chris is going to hopefully explain that in more detail in the next one. Okay? Okay, so what else does it tell you? So a corollary of this, kind of a proposition, you have to work a little bit harder. So remember, things that were dual cross sections were the BNS-invariant. We use that kind of idea to show that this whole cone lives inside of the BNS-invariant of the group. Okay? We'll sort of extend that to show that. And remember, this was the thing. We maybe wanted to know what the BNS-invariant was, and now we found a sort of big open cone inside of it. Okay, so that's kind of nice. And yeah, so what I've told you sort of proves that for the primitive integral classes, and then you have to work a little harder for the irrational class. And I didn't even define what BNS means for irrational classes, so you have to first learn that definition and then prove it for those things. You can do it. Okay, so a couple more things. Yeah. So remember now that if I'm in this cone, then I have cross-section. This is, if I'm a primitive integral class in this cone, I'm dual to some cross-section, and I have a first return map, F theta, remember. Okay, this sort of picture, this cross-section thing, gave me this HNN-extension splitting of my group, if you recall. So, this was what we talked about before. And remember, we wanted to study these monodromies, so this corresponding to different splittings. So these cross-sections are giving us splittings, and we want to understand these things. And the point is they're sort of coming from these nice first return maps. So if you could say something about these first return maps, if I say something about these. That's the idea. Okay, so here's another theorem. That this characteristic polynomial, this specialized polynomial is the characteristic polynomial of the first return of the transition matrix. Of that first return map. Okay, so somehow this polynomial knows about the first return maps of all of these cross sections to itself, you know, if you sort of set things up correctly. And it also turns out these maps are nice. So this map is an expanding irreducible train track map. That's another thing you can show. So that's another example of, if you start with something nice, an expanding irreducible train track map, now you're looking at these other vibrations, other cross sections, well, their first return maps are also nice. Expanding irreducible train track maps. Okay, and because of these two things, well, that means that this function, h of u is really the logarithm of the spectral radius of the transition matrix of that first return map, and because the first return maps are related to this monodromy, that tells you that e to the h of u is this function that I introduced a very long time ago, the stretch function for the various monodromies. Okay, so remember, every splitting, you have this monodromy here, you can calculate a stretch function called that lambda of u, and the point is this function h I defined is exactly calculating that for you. Okay.
So that's true even if it's not, the kernel isn't finally generated, but it's the other case.
Yeah, it's even true when the kernel's not finally generated. Yeah. And I should say here that, that's not a good point to say that, there's a sort of another polynomial, or another construction of a polynomial by Teichmueller together with the Algom-Kfir-Hironaka-Rafi. So they have sort of a different construction of a polynomial. And they do some similar things. In particular, their polynomial also calculates these stretch functions. Anyway, there's lots of relationships between these two approaches. So that I don't really have time to get into at the moment. So let me just say one more thing in the last minute. Okay, so think back to these algebraic questions we had in the beginning. We sort of wanted to know, when do you get nice splitting? So this cone is sort of telling you when you're going to get nice splittings. And it's also telling you about the dynamics of these monodromies in that case. So the final thing is that you can show this containment is actually onto a component. So this thing is a component. Of BNS-invariant. Okay, so it's some one connected component of it. And I think, an interesting question is whether maybe every component of the BNS-invariant looks like this is where these come. So that, I think, is an interesting question, which I still don't know the answer to. But I think we have time, so I should stop here. Thanks.